Right, good afternoon students, and welcome to Gonzo Physics. Once again, there is no pause on my document visualizer, so I can't stop. Once I've started, I have to keep going. If anybody's counting, it's Wednesday, the 1st of April. It's not been a very good week so far. Yesterday, the computer crashed. And it's taken a full 24 hours to get it back up again. This strange, brave new world in which we find ourselves is beset with IT. It's all about IT. It is for me anyway. Right, so I've got the computer back up again, so I thought I would make another lesson while the going was good for you to keep going with our Unit 2. Now, where we're at the moment, or where you should be at, is that the last activity that you did was exercise 2.3a, which was the exercise about lenses. Now, some of you have submitted that to me. I graded it and returned it, so you should have seen that through Fronter. I have or will provide the solutions to that, or my solutions to that, just as soon as I can get them scanned and uploaded. I was just about to do that when the computer went down. So you should have done exercise 2.3a. You should have got back your graded work. When you've got the solutions, you could review those questions. That means go through them and look at them again and iron out any sticking points that you have, and that should put you in a good position to move on then to the second part of lenses, or the last section in lenses, which is about defects of vision. Right, okay, now defects of vision, the reference for this, by the way, I haven't put that on here, but I'll put it on here. It's Carson and White, that's our textbook, and it's page 121 is when it starts. Now, I think this is a difficult topic. In fact, I find this is one of the most difficult topics in the whole of AS. So that's why you need to be confident about your lenses before you move on to this. And it might take a couple of goes through this to get your head around this. Okay, for this lesson, I've uploaded, or will upload along with this, some blanks, some partly made diagrams, which you're going to need to use during this exercise, or during this lesson. So you might want to pause at this point and download those things and print them out, because you're going to need them. You can do without them, but it would help if you had them. Okay, let's see what we've got then. Right, we are learning. The learning objectives in this lesson are to define what we mean by magnification as the ratio of image height to object height. M for magnification equals HI over HO, image height over object height. And also to recall and use the equation M equals V over U, where V and U are image distance and object distance respectively. Now, we really should have covered those points in a previous lesson, but we're going to fit them in now. You did need them for exercise 2.3a, but you seem to figure that out okay. Going along with that is the final point here, which is to perform calculations involving the power of a lens. So what do we mean by power of a lens? And then the meat of the lesson is in the middle here. Describe the use of lenses to correct myopia and hypermetropia, which are the two defects of vision. And perform calculations on the correction of long and short sight, which are myopia and hypermetropia respectively, including a calculation of the new range of vision. So we have some terms to define. then we have to describe how these conditions can be corrected and calculate the lenses required to correct those conditions. That's what it's all about. Now, in order to do that, we're going to go through the following steps. First of all, we'll define magnification and power of a lens. Then we'll describe how the normal eye works, how it forms an image. Question 4, or activity 4, is to describe the problem of a myopic eye, in other words, a person who has short sight, and how it can be solved using a diverging lens. Then we'll do a calculation on myopia. Now I might actually stop at that point and do the second condition in a subsequent video. We'll see how we're getting on. Point 6, to describe hypermetropia, which is long sight, and how it can be corrected using a converging lens. And then we'll do a calculation of the lens required to correct hypermetropia. And then that will leave you in the position to do exercise 2.3b. Okay, so if you download the worksheets, then you will find that they look like this. Here's the first one. Now, this is just a little starter to remind us about how the human eye, what the structure and function of the human eye is. So this is a Key Stage 3 worksheet. You might even have seen it before. Okay, so if you take the human eyeball, it looks like this. And if you took a cross section through it and looked at it, then these are the various parts. So that is the lens. So as I said, you could have, I've copied these myself. You could copy them too. You can copy them, don't they? So they are. You can copy them too and fill this in as you go along. Right. This is the lens. At the back of the eyeball, this is the retina, which is like the screen on which the image is formed. The front covering, the transparent covering at the front of the eye, is the cornea. This little bit here is the coloured part of the eye that opens and closes to control the amount of light that enters the eye, and that's the iris. And the hole in the middle of the iris that we see if we look in the mirror as a little black hole is the pupil. Okay, and that's all we have here. Now the eyeball is, that's about actual size actually. It's about a couple of inches across. It's filled with clear liquids which are called the vitreous and aqueous humours, which are basically clear liquids through which the light can pass. The lens itself is tissue. It's living tissue, as is the cornea, but they're both transparent. The one thing we haven't labelled here are these things here. These are the muscles. There's a ring of muscle going right the way around the lens, and it's called the ciliary muscle, C-I-L-I-A-R-Y, and it holds the lens in position, and also when the muscle contracts, it squeezes on the lens and changes its shape, which is basically the mechanism that the eye uses to focus. Okay, what does it say down below? Fill in the spaces below using the words in the box. Right, light from the window shines on this paper. What does it do? It reflects off the paper and enters my eye through the pupil. The light is bent or refracted by the lens so that the image is focused on the retina. And in bright light, the pupil gets smaller, letting in less light. Okay. So yes, you might remember then, this is basically the way the eye works. Light from some object passes through the cornea and through the lens. The lens, actually with the help of the cornea, focuses the light on the retina at the back of the eye. The lens has to form a sharp image on the retina. The retina then acts like a screen, but it's a kind of a smart screen because the retina is basically a layer of photosensitive or light-sensitive cells which can detect the light and pass the image back to the brain via this here, which is the optic nerve. So refraction actually happens twice in the eye. It happens here at the cornea because, as you can see, the cornea is curved. So the curved surfaces of the cornea, at least the front surface of the cornea, acts like a lens or as a lens and refracts the light as it passes through it. When the light hits the actual eye lens, it's refracted further, and it's the combination of refraction of the cornea and the lens that forms the sharp image on the retina. The iris's function is to control the amount of light that enters the eye and therefore the brightness of the image, and it is also a muscle basically, and as the muscle contracts and relaxes, it increases and decreases the size of the pupil, which in turn controls the amount of light entering the eye. The ciliary muscle, as we've mentioned, it squeezes the lens and changes its shape, and that's what allows the eye to focus the image on the retina. Okay, we can try a little trick while we're at it, which is this. Now, if you look at the retina, you can see that basically the retina runs right the way around the back surface of the eyeball, and it acts as the screen on which the image is formed. Now, the nerve impulses from the retinal cells are passed through nerves, and the nerve bundle that passes out from the eyeball here is called the optic nerve, and it passes the impulses, passes the signal to the brain, and the brain then processes the signal so that we see what we see. But where the optic nerve leaves the eyeball, there aren't any light-sensitive cells, so there's a little blind spot just here. And you can actually pick that up with a very simple trick. Now, you'll have to, I don't know if it'll work out with on the screen, but you can try this for yourself. If you just get a bit of paper and you put an X and a dot about 5 centimeters apart. Then, if you close one eye and focus on the X, and I have to move it across a bit to do this, then move your head, your eye, down towards the paper, keeping your eye fixed on the X. And what you should find is that the dot at a certain point just disappears. So if you're looking at the X, the dot has vanished. And that's because the image that's formed of the dot in your eyeball is falling right on the blind spot. Therefore, it doesn't get picked up. So you have a little blind spot in your field of vision. You're not aware of it really, where no information is being picked up. It works with both eyes, and it actually will work with the cross as well. If you focus on the dot and then zoom in on move your head in until the X disappears. Not quite so good with the X. Works better. Right. The right eye will make the dot disappear. The left eye will make the X disappear. So you could experiment a little bit with that and get to see what that does. Okay. Now, the next few pages, what I've done here is I've done some little diagrams with the outlines in place so that you can draw and annotate onto the outlines. So this activity is to examine the function of the normal eye and see how it works, and then to examine what is not working right in a short-sighted eye and in a long-sighted eye, and how it can be corrected. To do this, then, we're going to draw and annotate a series of diagrams. So what you should do is download and print these diagrams, or just do them from scratch, and we're going to draw and annotate, and you need to draw and annotate along with me. Okay, here we go. This could go badly wrong, of course. So, I'm going to put a title on this. I'm not going to attempt to go through bits quickly because that was extremely difficult to achieve in editing. It's all going to be one. So if you want to jump ahead, you can do so. Okay, so in figure 1, we're just going to look at the normal eye. Now, by normal, what we mean is an eye that can focus on objects that are nearby and objects that are far away and objects in between without the need for lenses, either spectacle lenses or contact lenses or any other kind of correction. Okay? Now, of course, there is no normal, and in fact, I think the term is politically incorrect these days, but with that. So, in a normal eye, as we know, we see things because of rays of light reflected from the object and entering the eye. Now, as we've said already, what we're trying to show here is this is the eyeball. This is a rather exaggerated version of the cornea, which sticks out a little bit at the front. Here's the lens held by the ciliary muscles, and here is the iris, and here is the retina at the back of the eye. I think I'm going to work in pencil actually, just in case. Right. So light entering the eye suffers refraction at the cornea, and then it suffers a little bit of extra refraction at the lens. Now, the cornea is fixed, but the eye lens, although it's living tissue, the tissue is transparent and it's also flexible. It's a bit like a sort of jelly-like substance. And therefore, when the ciliary muscle contracts, it changes the shape of that muscle. And it can make it either thicker or thinner. Now, and when it does that, that process is called accommodation. So when the eye changes the shape of the eye lens to focus a sharp image on the retina, that process is called accommodation. Now, no, a better way of saying that would be this. So the eye can accommodate, the normal eye can accommodate objects at different distances. And the furthest point, the most distant object that the eye can form an image of is called the far point. And the closest point to the eye that it can form an image is called the near point. So you can do this experiment for yourself because it's what we do all the time. If you look up, and if I look up and look out of the windows and look across the rolling lawns of Spence Towers down to the lake with the swans on it, then I can focus quite clearly on objects at the bottom of the garden. So what that means is that my far point is at infinity. Now, that does not mean that it's an infinite distance to the end of the garden. If you remember in optics, infinity means any object which is more than a few meters away from you. So that could be a few meters away, or it could be many kilometers away, as far as the eye can see. So for the normal eye, or in my case, the corrected eye, the far point is at infinity. Now, if you then look down and say, look at your pencil, if you look at your pencil in front of you, you should be able to focus on that clearly as well. In other words, the eye can accommodate that. But if you bring the pencil closer to your eye, and closer, there comes a point where the eye cannot accommodate it, where the pencil appears to go out of focus. And no matter how hard you try, you can't quite focus it. So the closest distance at which the eye can focus on the pencil is called the near point. And our range of vision then is between the near point and the far point. The near point for a normal eye is usually about 20 to 25 centimeters away from the eye. And for our purposes, we'll assume that all eyes are the same, which of course they're not, but we'll assume that they are, and we'll assume that a typical near point is at about 25 centimeters. We'll take the typical near point as 25 centimeters. Then, as you look up and look at objects further away, the eye accommodates to those until, if you look at a distant object at infinity, the eye can accommodate that as well. So your range of vision is from your near point at about 25 centimeters to your far point at infinity. Okay, what is actually going on to do that? Well, when an object is at infinity, so let's suppose that we have an object at infinity. And remember that infinity means just a large distance, which is greater than a few meters. Okay. Now, if the object is way out here somewhere, then the rays coming from that object, when they arrive at the eye, they are effectively parallel. If you remember the little experiment we did with the pieces of string, if you have rays coming from a single point on a distant object, an object at infinity, then when they reach the eye, or a lens, which is relatively small, the divergence of those rays is so small as to be negligible. So we can say that the rays are effectively parallel. And when those rays arrive at the lens, they're going to get, or arrive at the eye, they're going to get refracted. Now, we can show the refraction in two parts. They're going to get refracted quite considerably by the cornea. Now, in my diagram, the ray is going to magically pass through the iris, which it can't do. And then it's going to get refracted again by the lens. And I'm going to make it miss the optic nerve, so it does actually fall on some cells that can focus it. Same thing will happen to this ray. That's a bit dodgy. Okay, so that looks a bit strange, but basically then, maybe I should change that. Okay, so what we're looking for is a double refraction, and then the ray is going to wind up somewhere here on the retina. Now in this case it is going to land right in the optic nerve, which is just too bad. Like so, more or less. Okay, So in order to focus a distant object, the eye doesn't have to do anything at all. The eye lens is fully relaxed or unaccommodated. And in a normal eye, when the eye lens is completely relaxed, parallel rays will be focused on the retina at the back. And that means that the length of the eyeball is equal to the focal length. Okay, so our eye has evolved to have a lens which has a focal length which is equal to the length of the eyeball. And therefore, an object at infinity will be focused on the retina. Okay, so the object is at infinity. Rays are effectively parallel. And the eye is fully relaxed. Or unaccommodated. And the eyeball length is equal to the focal length of the eye lens, or strictly the eye-cornea combination. And so a focused image is obtained on the retina. So therefore, you can focus on an object which is at infinity. So the far point is at infinity. Okay. Now you'll remember that when we did this experiment with a glass lens, the image that you obtain is real. You can see it on the screen. It's diminished and it's also upside down. So the image that is obtained is upside down. And the signal that goes to the brain is basically carrying an upside down image. But it's the visual cortex in the brain that processes that image and turns it right way up. Or at least so that we perceive it. So that's the business of the brain. Okay, figure 2 is if we place the object at the near point. And this is the distance closest to the eye, or the shortest distance at which an object can be maybe we should say image. Focused image. Can be obtained. Okay. Now, that's approximately 25 centimeters for normal eye. So here's the eye. I've simplified this time, just drawn the eyeball and the lens. So the near point would be, say, here. And if we represent the object as just a point object, because it's close to the lens, we can no longer suppose that the rays are parallel. They are actually diverging like that. Now, again, I'm not going to show the double refraction that occurs at the lens here. We'll just show it happening at a single refraction as if the lens was a single line. So, if the eye is to be able to focus those rays, well, the relaxed eye wouldn't be able to do it. The relaxed eye can focus parallel rays, but it won't be able to focus diverging rays. To do that, what it has to do is it has to get fatter. It has to be the ciliary muscle contracts, that squeezes on the lens, and the lens gets a little bit fatter and more convex. That reduces its focal length, and that makes it possible to converge rays which are diverging when they reach the lens so that they actually meet at the retina. And if that's the case, we will then see a sharp image on the retina. So the near point, approximately 25 centimeters from the eye, that's the shortest distance at which a focused image can be obtained. And the way that the eye is doing that is that the ciliary muscle contracts, making the lens, well, I'm going to say fatter. That may be politically incorrect as well, but what we mean is more convex. And therefore stronger, so that it's able to focus these rays on the retina at the back. Now, at the near point, the eye is, as the ciliary muscles are fully contracted, the lens is fully squashed as fat as it can get, and therefore you can't do any better than that. If you move within the near point, the eye lens can't accommodate to that. So in this state, the eye is fully accommodated. Okay. And basically what your eye does is it moves between these two states. It moves between being fully accommodated when you're looking at something close to, and fully relaxed when you're looking at a distant object. And as your focus changes, you look up and look out of the window, you look down at the page, your eye is moving between these two states. And you can focus on objects in between by accommodating, by squeezing the lens by different amounts, and therefore you can focus on objects at different distances. And the range of distances at which you can focus is the difference between the near point and the far point. So I'll just make a note of that. So the range of vision is the distance between the near point and the far point. And again, for the normal eye, the range is from about 25 centimeters, the near point, out to infinity, which is a few meters and beyond. Okay. Now, gone 34 minutes at this point. I think I'm going to pause, which might mean stopping this video at this point, and in the next video look at what happens in the myopic eye. So what you should have then is two diagrams so far, one for the normal eye and one for the well, two for the normal eye actually. For the normal eye, focusing on an object at infinity, and another one for the object at the near point. Okay.